All right, so we've talked about solving linear systems, and we've talked about solving the least squared problem. And now the next topic is going to be eigenvalues and eigenvectors. And again, I said that I want to go to chapter 5 and not spend too much time on 4 and maybe come back later. But I will need to say a few things from 4. So in particular, let me remind you that eigenvalues only make sense if you have a square matrix, right? So we're going to assume now that A is n by n, and then we want to solve AU is lambda U for lambda real or complex and U that's the eigenvalue problem in general. Um, so the way to think about this is to move things to one side. And then that way you get a homogeneous system. Of equations. And homogeneous systems are always consistent. You know, there's always the solution U equals 0. The question is it the unique solution, in which case, because of this condition here, in which case there are no eigenvectors, or are there infinitely many solutions? And so the eigenvalues corresponds to the lambdas that make this system have infinitely many solutions. And that happens when the rank falls below n. Right? So if the rank is n, then there's n pivots in the reduced row echelon form, and then the unique solution is the 0 solution. If the rank is deficient, then you will get infinitely many solutions, and so lambda is going to be an eigenvalue. Another way to think about this, because we are in a situation of square matrices, a square matrix has 4 rank if and only if it's invertible. And so another way, alternatively, we can look for lambda such that the determinant of A minus lambda I, right? So it's equivalent to look for this is actually, it turns out that this is a polynomial in lambda. called the characteristic polynomial. And so the eigenvalues are exactly the roots of the characteristic polynomial. Um, and not hard to see. So if you write A minus lambda I, it's going to look like this: A11 minus lambda A12. Etc. Right? And so, and the determinant, there is a formula for the determinant, right? Where you, if you call this, let's call this matrix M, right? The formula for the determinant is that you take, for each column, you're going to pick a row, right? So pick a row, sigma j in each column j, and take a product. But so for every column j, you pick a row, but you are not allowed to repeat, right? And so sigma needs to be a permutation. And so you got to sum over the set of all permutations on n objects. And then permutation have a sign, and you need to also multiply by the sign of the permutation. So that's the general formula for determinants. I don't know if you've seen this before, but have you seen this formula before?
I haven't seen this one before.
Yeah, I'm not sure. I don't think so. I was just trying to reason out if this was cofactor, how it's presented with cofactor expansion or not. But I don't think so.
Well, okay, so let me maybe remind you. So determinants are linear in each row and in each column, right? You can add things. So let's see. If your matrix M is made up of columns, right? V1, Vn. And each column is, well, a linear combination right? Each column is a linear combination of standard basis vectors. Then when you take the determinant, by linearity, you can take out the sum. Right? And then you can repeat. Now you can use the linearity in the second column and take out so let's call it, just call this VI1 and then VI2, determinant of VI1, VI2, V3, right? So does that make sense so far?
Yeah.
All right. So, and there's two sums here. Now you have to sum over I1 and I2. So if you continue that way, in the end, you're going to get a gigantic sum here, I1, I2, IN, from 1 to n, VI1, 1, VI2, 2, VIN, and then you get the determinant of VI1, VI2, VIN. Now, the first thing you notice here is that if you repeat two indices, then this determinant is going to be 0. So all of these I1, I2, IN, they have to all be distinct. Otherwise, you get 0. So that means that you need to choose a permutation of the indices. And so that means that these are permutation matrices. And permutation matrices have determinants -1 or 1. And that's basically the sign of the permutation. Okay, so that's what I have written. So you pick a permutation, you take the product. That's another way of writing it is like this. Sigma j is the permutation here that you pick. You do the product of those entries, and then you multiply by the sign of the permutation, which is the determinant of this entry. That makes sense now?
Yeah, thank you.
Yeah.
All right, so in every column, when you pick a row, there's a chance that you pick the entry that has a lambda in it, right? But you might not, right? So the worst you can do is pick lambda n times. And so that shows that this EA lambda is a polynomial of degree n, exactly n, because of course you can pick in this, when you do the determinant, and and you can decide to pick the diagonal term in every column, right? And in that case, you're gonna get, especially let me actually back up here. The PA lambda is not this one, is this. It's slightly better. So let me show you what the difference is. Yeah, this is not quite PA lambda. They are different by a sign, but the sign depends on the dimension of the matrix, right? Because when you pick the diagonal elements here in this product, you're gonna get minus lambda times minus lambda n times, right? Minus lambda to the n. So in order to avoid that, I do lambda I minus a, and then I'm gonna get lambda to the n as my leading term. So that's gonna be the n, and then there's gonna be lower order terms. So the leading coefficient is you write it like that. That makes sense?
Mm-hmm.
Yep.
All right. So okay, so it's a polynomial of degree n, and in particular, there is something called the fundamental theorem of algebra. You guys remember what it says?
That for any polynomial of degree n, it has exactly n complex roots.
So it has exactly n roots in C. So there's always exactly n eigenvalues. But this creates a little bit of a problem for us because A is, A for us is always going to be real. Of course, we could assume A to have complex entries, and we get the same polynomial of degree n, but we want to start with a real matrix. And so if you get a complex root, then you also get an eigenvector that will have complex entries, right? So that's not ideal, but all right. So let's assume that we are in the in the best case scenario. Say that you have exactly n real roots. Distinct. Then in that case, the eigenvectors form a basis. well, they are going to be linearly independent. Right? And so they form a basis, and you can change variables. And that's called diagonalizing, right? So change variables. And you can write a S and inverse lambda is diagonal. And S contains the basis vector, the eigenvector. Right, so in this case, we say that A is diagonalizable. But unfortunately, that's not always the case. Of course, having n distinct real roots is a sufficient condition for diagonalization, but not necessary. It can be diagonalizable and also not have n distinct real roots. Questions? All right, so let's do an example that's in chapter 4. Called mechanical vibrations. So the idea is you have, let's say, a wall and some kind of a coil spring. And there's a rod here and a mass that's allowed to move horizontally without friction. And let's say that the spring has a constant K1. We will keep track of the position using the X variable. And then maybe this is connected to another mass, M2, position X2, etc. Mn. So that's K2. Kn. And also, let's assume that these masses are connected to a damper, V1, V2. So that's kind of the system. And one way to analyze this system is to use Newton's law. F equal ma, right? So what is the acceleration here? Well, the acceleration is the second derivative. I'm going to use physics notation and use little dots. This is the acceleration of the ith mass, and it has mass mi. And now I need to talk about the forces that act on that mass, right? There's something called Hooke's law, I think, for springs. The acceleration is basically the negative of the displacement times this constant k. So ki xi minus 1 minus xi. Okay, so this is ki is the spring that comes before the mass mi, and this is minus the displacement here, plus ki plus 1, xi plus 1. This is the regular displacement. All right. And then the damping, Bi, is kind of like an air resistance. The faster you're going, the more, right? So it actually is proportional to the velocity. Okay, does that make sense?
Yeah, I missed why we had two terms for displacement.
Well, because there's, so here is mi. There's a coil here coming in and a coil coming out.
Oh, sure.
I mean, except for the last one. So we need to be careful. But right. So, well, the good news is that this is linear. And so we can use matrices to express this, right? So we can maybe write it as m x double dots is equal to minus k xt and then minus b. Right, so what are the matrices? M is just the diagonal matrix with the masses. And B is the diagonal matrix. Okay, so that's the mass matrix. And this is the damping. And then K, you need to work a little bit harder for that. It's called the stiffness matrix. And all right, so notice, how does it act on the diagonal term, right? On xi. On xi, we need to multiply by ki and then also by ki plus 1. So k1 k2. We'll start out like that. And then, so the first term doesn't have an I minus 1 because there's a wall there, but it has an I plus 1. times ki plus 2. So that's going to be minus k2 and then minus k2 here, k2 plus k3, k3, etc. Right? So this will continue down like that. And then at the end, let's be more precise. At the end, you're left with minus kn, because there's no kn plus 1 term. All right, does that make sense?
Mm-hmm.
All right, so first, what do we notice? This is a tridiagonal. That's a good thing. And this is a standard trick now to change this second order ODE, right, to a first order ODE. So let's do that. In physics, this would be, it's called the phase space. You go to phase space. So you define a new variable, y, that it has both the position and the velocity. It keeps track of both. Position in physics is position and momentum, right? You multiply by m, but I don't know how much physics you've had. But if you've had any Hamiltonian mechanics, you will recognize this. All right, so with that, what happens when you take the derivative of this new variable? Well, you're going to get the second derivative of x here and the first derivative there, right? And then you can just replace the second derivative by solving for x, double dot here, multiplying by the inverse of m. So we're going to get minus m inverse b dot minus m inverse k x. And so how is this a first order? Well, we can interpret this as the result of a matrix multiplication where, let's say, we have some blocks, minus m1 in m inverse b minus M inverse K, and the identity is 0. So this is a 2n by 2n matrix. The blocks are n by n. And matrix A. And then the problem becomes standard dynamical problem, y dot equal some matrix times y. This is a first order. E. And usually you need some initial conditions. You need an initial velocity, an initial position, and the system evolves from that. That makes sense?
Mm-hmm.
All right, so let's assume that A is diagonalizable. Right, so then we can write it as S lambda S inverse as before. And then y dot is going to be S lambda S inverse of y. And we can multiply by S inverse on both sides. And then because S inverse is a matrix, right? So this is a linear operation. You can switch it with the operation of taking time derivatives. So actually you can write this as S inverse y of t dot, right? And so if you call this, sorry, this is the, if you call this, say, z of t, then z dot of t, sorry, that's not an A now. This is a lambda. Okay, so lambda, maybe I should put feet on it. So lambda z of t. All right, but that's very easy to that we sort of decouple the various ODEs in the system of ODEs, and basically now we want for every j, zj dot of t should be lambda j zero, because lambda is a diagonal matrix. Zj, right? And so these are very simple, you know, population dynamics type things. You can separate, you know, do you remember how to do this? EZJ, T, DT, lambda J, ZJ, T. Basically separate the variables. And then you integrate log constant, et cetera. Then you exponentiate. So ZJT JT becomes VJ0 e to the lambda j. Right? And you can then go back and write y as S times diagonal matrix e to the lambda 1t e to the lambda nt. So that's the general solution to this type of equation. And just to give you an idea, let's do the one mass case. In that case, there's only one damping constant, one mass m, one constant k. And so it's just a 2x2 matrix that looks like that. Let's compute the determinant of A minus lambda I. Minus B over M. Sorry, right. Minus and the minus cancel, so lambda. The minus and the minus cancel. Get that. Or in other words, lambda squared all right, so we have a nice quadratic polynomial. We can compute the discriminant, right? B squared minus 4AC. All right, so that's going to be B squared over M squared minus 4K over M. And if I factor out B squared M, something like that. And then basically lambda is 1/2 minus B over M plus or minus, sorry, M squared. Yeah, M squared. So minus b over m, square root of 1 minus 4 b over 2m minus 1. That's a minus. All right, so the key now is the question, is the radical, the thing under the square root, positive or negative? So 1 minus 4km over b squared is negative if and only if 4km b squared is greater than 1, right? And in that case, we get two complex conjugates, right? Because the imaginary units comes out of the square root, and then there's a real part. So this is called the underdamped and I think it does something like this. And then if instead 1 minus 4km b squared is positive, then 4km over b squared is less than 1, right? This is the overdamped case. And in that case, you have two real roots. So e to the minus, e to the minus lambda t will actually kind of decays like that. In fact, because you get two negative roots. If you look at the expression, there's a minus here. And this thing here, 4k, this case is going to be less than 1. So it's not enough to make this positive, this minus 1, when you take the square root. All right, so, and of course, then there's the case 1 minus 4km over b equals 0. This is called critically damped. And we'll not discuss this case as yet. So that's where the Jordan blocks come in. All right, so I ran out of time, but basically the idea is that when you have this kind of oscillations, it's because there's some complex roots involved. All right, questions?
Mhm.
Right, because e to the IT, you remember, is cosine t. That's how you get the oscillation, those cosines and so
Yeah.
on. All right. So let me stop here.